There's no question about it. Over the past 5 years, the development and testing process for Starship has never ceased to include an appreciable level of drama. In the second half of 2024, SpaceX conducted 3 consecutive test flights which demonstrated Starship's ability to perform a controlled atmospheric re-entry, followed by a precise landing in the Indian Ocean. While each attempt was undeniably better than the one before, it was clear that major changes were needed to certain features of the ship's design before they could progress any further. So, leading up to the 7th test flight in January of 2025, there was a lot of hype built up around the debut of SpaceX's upgraded version 2 Starship. The highly anticipated design changes were expected to be a massive improvement that would enable the ship to survive the extreme heat experienced during re-entry in a condition that would allow SpaceX to begin recovering and eventually reusing the second stage vehicle. Unfortunately, this incredibly important milestone has been put on hold after what was expected to be a seamless transition resulted in the catastrophic destruction of both Ship 33 and Ship 34. The similarity of these events was such that if not for the additional camera views provided on Flight 8, it would have felt like deja vu. Never before have we seen SpaceX encounter an issue that they weren't able to either completely resolve or demonstrate major improvements on the very next flight. So, after exceptionally rare and nearly identical back-to-back failures, a lot of people can't help but to wonder, is version 2 of the Starship completely cooked, or is there some misunderstanding about the severity of this situation? If you're looking for answers to that question, then you've come to the right place. My name is Zach Gold, and this is another CSI Starbase Deep Dive Investigation. Hey Starship addicts, welcome and thanks for joining us. I'm sure many of you who clicked on this video are wondering, good lord, how could it possibly be necessary for an episode about Starship's recent in-flight failures to be 90 minutes long? Well, to tell you the truth, I didn't think it was necessary either at first, but as it turns out, there is a huge list of questions that we need to answer. What is the real source of the problems that have caused the destruction of the ship on Flights 7 and 8? Why did this problem never occur with the previous version of the ship? Why did the attempts to mitigate this problem after Flight 7 have little to no effect? Why was this issue not able to be detected during pre-flight testing 2 times in a row? And is there anything SpaceX can do to ensure this will never happen again without reverting back to the version 1 propulsion system? Is this really even a problem with the upgraded V2 design? Or should we actually be placing the blame on the same usual suspect that's caused a majority of SpaceX's setbacks over the past few years? Is this some uniquely crazy occurrence that's exclusive to Starship? Or is there something we can learn from historical examples by examining NASA's experience with Titan II, Saturn V, and the Space Shuttle? And finally, we will use the answers to all of these questions to analyze the list of potential solutions that SpaceX may incorporate going forward. By the end of this episode, it's my goal that if Starship fails again on the upcoming 9th flight test, you will understand why. And if it succeeds, then you'll have a good idea of the steps they likely took to avoid another disaster. I understand that a 90-minute documentary may exceed the attention span of some viewers. So in case you have to watch this in multiple sittings, I've included timestamps in the video play bar and description. With that, let's get into today's ridiculously deep dive investigation.
Who are you talking to?
The fuck? Can I help you?
Yeah, you got this delivery here. What's up with the casket?
Oh, check it. Huh?
Okay. I see what you did there.
Yeah, I thought it was pretty clever.
Well, we might want to change the address on these packages.
What do you mean?
Today's demo day.
For here?
Yeah, I didn't tell you. Today's demo day. We got about an hour.
Oh, nah, I need at least an hour 15.
I'm going to need you to start packing everything up. I'll give you an hour. We'll talk to the big guy, see if I can get you that extra 15.
All right, appreciate it, sir.
You got it.
All right, well, this is literally the worst possible timing, but we're just going to have to make the most of this situation and knock out 2 birds with 1 stone while I get this place packed up. Anyway, I think the best place to start this investigation is with the official statement provided by SpaceX after the Flight 7 anomaly, which explained the chain of events that were observed by the onboard cameras. I'm just going to read this directly from the report. After vehicle separation, Starship's 6 second-stage Raptor engines powered the vehicle along its expected trajectory. Approximately 2 minutes into its burn, a flash was observed in the aft section of the vehicle near one of the Raptor vacuum engines. This is important detail number 1. Roughly 2 minutes later, another flash was observed, followed by sustained fires in the attic. These eventually caused all but one of Starship's engines to execute controlled shutdown sequences. This is actually really good information, but perhaps the most important detail is where they identified the root cause of the failure as a harmonic response several times stronger in flight than had been seen during testing. Now, depending on how closely you've been following this situation, there's a good chance that you've heard this before, and probably still to this day feel like this is a rather vague statement. And I agree. So I think the most important thing for us to do is get a conceptual understanding of the term harmonic resonance. Let's start off by defining resonant or natural frequency. Natural frequency describes the rate at which a solid object or system oscillates when disturbed from its resting position. For example, when we take this decorative bottle and tap on the side of it, the sound you're hearing represents its natural frequency. The natural frequency of a solid object will change based on its physical properties. For example, if the shape, material, or mass of the bottle changes, its natural frequency will change as well. These two bottles are nearly identical, but this one has less mass thanks to the fact that someone left it half empty. When we tap on the side of this, you can hear the difference in tone that results from the change in mass. This concept applies to fluids as well. The air inside of the bottle has a natural frequency, and when I blow over the top of the opening, the sound it produces has a different frequency than the bottle itself. Now, when we take the half-empty bottle, the increased height of the air column causes it to vibrate slower. So, as more fluid is removed, the natural frequency of the air is reduced, causing it to produce a deeper sound. Many solid objects have multiple natural frequencies, each corresponding to a different mode of vibration. The fundamental mode is the lowest natural frequency where an object wants to vibrate. In this example from Geoff Martin that I've linked in the description, you can see a string being moved up and down using a mid-range speaker. When the string is oscillated up and down 11 times per second, or at a frequency of 11 Hz, it reaches the first resonant mode of the string. In other words, this is the lowest frequency it wants to resonate at. You can see this creates a single standing wave in the string. As the frequency is increased, destructive interference from the reflected wave patterns begin to cancel each other out. This continues until the second resonant mode is reached at 22 Hz. The area that seems to be stationary is the node, and the top of the standing wave where the amplitude is highest is referred to as the antinode. As you step through each sequential resonant mode, from 33 to 44 to 55 Hz, you can see that the number of nodes in the waves increases as well. In this example from Steve Mould, you can see this concept applied to a fluid where sound waves are traveling through a manifold containing butane gas. This time, when the frequency of the sound wave matches the natural frequency of the gas, the vibrations cause fluctuations in pressure, which reach a peak at each of the antinodes and remain constant at the nodes. This leads us to the concept of harmonic resonance. Harmonic resonance occurs when a system is subjected to an external force or vibration that matches its natural frequency or the frequency at which the system naturally tends to oscillate when disturbed. When this happens, the amplitude of the oscillations can increase dramatically, sometimes with catastrophic results. There are some great real-world examples of this. One you may be familiar with is the historical Tacoma Narrows Bridge, which was the third largest suspension bridge in the world at the time of its collapse in 1940. Similar to the string, a bridge is a mechanical system with its own set of natural frequencies, which are determined by its structure. This includes its length, material, stiffness, and mass. These frequencies are like the preferred vibration modes of the bridge. For example, a suspension bridge might sway side to side or up and down at specific rates, depending on how it's built. Now, if an external force like wind, footsteps, or traffic applies a periodic push or pull at a frequency that aligns with one of the bridge's natural frequencies, it can start to amplify those vibrations. This is resonance. If the energy keeps coming in at that sweet spot frequency, the oscillations will continue to grow larger. Unfortunately for the Tacoma Narrows Bridge, this resulted in the collapse of the structure.
Fortunately, the only casualties were a car stalled on the bridge and a dog.
Alright, now let's apply this same concept to a rocket. In the aerospace industry, the equivalent harmonic resonance phenomenon is formally known as coupled structure propulsion instability. The word coupled is very important because it highlights the fact that the propulsion system and elements of the vehicle's structure are working together to cause problems. In some ways, it's similar to the bridge example, except the vibrations occur along the longitudinal axis of the vehicle. When these vibrations become severe enough, they will actually cause the rocket to bounce up and down like a pogo stick. Hence the reason this phenomenon is commonly referred to as POGO for short. In order to truly understand this harmonic resonance issue, it's really important to identify the origin of the vibrations in the system. That might seem like a no-brainer, and I'm sure most folks would say, "Oh, well, it comes from the engines, duh." And this is partially true, considering all combustion engines vibrate during operation to some degree. But this is perhaps a massive oversimplification, and the real explanation is a bit more interesting and complex. Depending on how you look at it, the source of this vibration can actually be traced back to internal conditions inside of the propellant tank. Using this basic example from eager space, we can visualize the pressure differential existing inside of the liquid-filled tank. For the sake of this explanation, let's say at the top of the tank the pressure is 0, although in reality it would be much higher given the ullage pressure in the tank. At the bottom of the tank, which will experience hydrostatic pressure from the weight of the fluid column above, the pressure will be equal to 1 atmosphere. Connected to the tank is a pipe leading downwards, which you can think of as the methane feed line on a Starship. We sometimes refer to this as the downcomer or transfer tube. At the bottom of that feed pipe, the hydrostatic pressure increases to 2 atmospheres. These values represent the pressure while the vehicle is stationary on the ground, with the Earth's gravitational force pulling down on the fluid column. So after liftoff, when the vehicle's speed is increasing with an acceleration of 1g, the total acceleration pushing down on the fluid column will be 2g's. This doubles the pressure experienced at each location. As the acceleration continues to increase, the pressure will increase with it. One thing that will cause the acceleration to increase is obviously a commanded increase in thrust from the engines by the flight computer. But the acceleration will also increase without any change in thrust at all. As the propellants are consumed during flight, the mass of the vehicle will decrease, which causes the thrust-to-weight ratio to increase. The vehicle begins to accelerate faster, which will cause the hydrostatic pressure of the fluid to rise even further. This increase in pressure can have an interesting effect on the propulsion system. Let's use Falcon 9 as an example. Before max Q, Falcon 9 throttles down to reduce its acceleration and maximum aerodynamic pressure. After passing through max Q, it immediately begins to throttle back up. The increased acceleration is followed by an increase in pressure. The key detail is that it's not instantaneous. Instead, it produces a pressure wave traveling at the speed of sound from the top of the tank down to the bottom of the downcomer. When this pressure wave reaches the turbo pump, it can cause a spike in back pressure to the pump inlet, which, if left unmitigated, will briefly increase the flow of propellants to the main combustion chamber and cause a surge in thrust output from the engine. This is a great example just to get the basic point across, but as it relates to POGO, it's actually the smaller random changes in acceleration that we are truly worried about. If you were to view the raw telemetry data for any liquid-fueled rocket, you will see that the power output will not be smooth, but will instead have small variations. These variations represent combustion instability, which occurs naturally in every engine. Some engines have smoother combustion and others are more rough. These are unique characteristics for every rocket engine. In fact, if you had access to this data for an unknown engine, you could probably use it to identify what type of engine it is, kind of like a fingerprint or DNA sample. Anyway, to complete the cycle, the variations in pump inlet pressure cause combustion instability, which creates variations in thrust, resulting in a spike in acceleration, which then creates another pressure wave in the fluid column. This pressure wave travels back down to the pump, causing another surge in pressure, followed by another surge in thrust output. The timing or frequency of this is very important. If a pressure wave arrives at the right time, you can end up with a repeated oscillation in thrust and acceleration that will continue as long as the proper conditions exist. This behavior is what causes the engines, internal components, or the entire vehicle to bounce up and down. There are several factors that contribute to the strength of these pressure waves. The height of the fluid column in the tank, the density of the propellants, and the length of the pipes are all very important. Increasing any of these parameters will also increase the strength of the pressure wave. When the tanks are mostly full, variations in thrust have a smaller effect on acceleration, but as the propellants are consumed during flight and the mass of the vehicle decreases rapidly, the same variations in thrust will have a greater effect on acceleration and create stronger pressure waves. Having more engines can actually reduce the fluctuations in pressure, especially if the individual feed lines are pulling from the same downcomer. There are several reasons for this. The feed lines for each engine may vary in length and flow path depending on the position of the engines. Using the booster as an example, Super Heavy has one large methane downcomer supplying all 33 engines. At the bottom of the downcomer is a sump, which is basically a common manifold for the individual engines. The feed lines for the center engines are very short and pull directly from the bottom of the sump. The middle ring of 10 have short downpipes extending from the sump, while the outer ring of 20 have much longer feed pipes. So engines that are all within the same group will have the same pump and line frequencies. And because there are 3 groups pulling from the same source, it makes it unlikely that they will all sync perfectly with each other or the vehicle structure. This desynchronizes the system and reduces the chances of a single, strong resonant feedback loop. Oscillations from the group of outer 20 engines might be out of phase with the middle ring of 10 or the 3 center engines, which will cancel out some of the pressure waves before they amplify across the whole system. So yeah, this is probably part of the reason why Super Heavy is such a f***ing boss and has not yet experienced these types of problems. But on that note, it theoretically becomes more susceptible to this issue during the 13-engine boost back burn, and even more so during the landing burn after it drops down to 3 engines. For rockets that use a multi-engine configuration, this problem seems to be a lot more likely to happen if each engine has its own dedicated feed line where there's nothing to disrupt the feedback loop. Not only do these pressure fluctuations affect the performance of the engines, but the resulting spikes in acceleration also have the potential to impart significant G-forces in various locations on the vehicle. With that said, this is a super important design consideration in rocket manufacturing because each component needs to be able to withstand whatever forces they're expected to encounter. The key word here is expected, because under the right conditions, this problem can become exponentially worse and quickly exceed those expectations you've designed around. And this is where harmonic resonance comes into play. If the frequency of pressure wave oscillations through the propellants begins to match the natural frequency of the main fuselage or any of the internal components, then you may begin to encounter some pretty serious problems. While the main superstructure may be able to handle this, the same may not be true for other components. Excessive vibrations reaching various onboard sensors like inertial measurements units, gyroscopes, and accelerometers can result in noisy data being sent back to the flight computer. This might make it difficult for the guidance system to distinguish real attitude changes from vibration-induced wobble. This could result in overcorrections of thrust or engine gimbling and cause the rocket to veer off course. Depending on how and where it's mounted, the actual flight computer itself can become damaged from excessive mechanical stress to various internal hardware components. The same is true for sensitive payloads, which are even more likely to be damaged. This includes human payloads as well. Strong vibrations in the crew compartment can impair their ability to perform important in-flight operations, and in extreme cases, it can even cause injuries or death. While this is important to keep in mind for the future, this doesn't really seem to apply to the current situation with the version 2 Starship. Now, if resonant coupling occurs between the pressure waves traveling through the propellant feed lines and a specific part of the propulsion system, the effects will be more localized instead of impacting the entire structure. This is fairly complex because it can manifest in many different ways. But based on the snippets of information released by SpaceX, this is probably where we should direct our focus. In the case of Flight 7, they mentioned that the excessive vibration led to increased stress on the propulsion system, resulting in propellant leaks. These leaks caused fires in the aft section of the vehicle, specifically in the unpressurized attic area between the liquid oxygen tank and the aft heat shield. Although it's yet to be confirmed as of the time of this episode, I think it's safe to assume that a very similar, if not identical situation occurred on Flight 8 as well. Either way, this is extremely helpful information when it comes to narrowing down the scope of possible explanations. But if we want to actually attempt to explain the potential options available for solving this issue, then we definitely need to narrow down the specific point of failure even further. To do that, we need to gather any additional information that's readily available to us. Let's start off with the most obvious question. This clearly wasn't a problem with version 1 of the ship, so what changes were made to version 2 that might be relevant to this situation? I have to be honest with y'all. Returning viewers to the channel know that I've been an order of magnitude more invested in Super Heavy development than the ship up to this point. So I'm sure you won't be surprised to learn that the moment it became clear that we would be seeing V2 ships nearly a full year before V2 boosters, I was pretty disappointed. Maybe even jealous. But after the outcome of the past 2 test flights, I don't know. Maybe everything really does happen for a reason. If this situation were happening with the booster right now, it would be far more devastating in my opinion. In the worst case scenario, it would either result in the loss of both vehicles during the ascent phase, or potentially cause serious damage to the pad if it happened during the landing burn. As I'm sure most of you are at least vaguely aware of, the version 2 ship featured thousands of changes from the previous design. Most of the external changes are clearly visible and therefore well documented. But there are also a ton of internal changes to the vehicle, a majority of which we will never learn about. Because of this, it's important to note that there are probably a multitude of additional factors at play here that we are completely unaware of. So just to be clear, any conclusions that we come to today are based on incomplete information. Apparently I have to give regular reminders that there is a ton of speculation involved here, or else some people will literally lose their minds. With that said, the only changes that we will concern ourselves with today are related to the propulsion system. If you want to learn more about the other upgrades, I highly recommend checking out the impressive series of articles posted on the Ringwatchers website, which I've linked in the description. Now, I typically use a ton of renders and animations to help explain these topics, but today, we have another awesome resource at our disposal thanks to the amazing folks over at morethan3d.com. This amazing 3D printed model of the late Ship 34 is ridiculously well designed, and because of the insane level of detail, we can actually use it to help visualize most of the concepts we will discuss throughout this investigation. In the meantime, let's quickly address the most relevant upgrades to Starship 2.0. Other than the redesigned flaps, the most obvious change to the ship was its increased propellant capacity. Through a combination of stretching the tanks and shrinking the payload section, the total capacity was increased from 1,200 tons of densified liquid methane and oxygen up to 1,500 tons. On its own, it's hard to relate this change back to the POGO situation, but it's interesting to note because of the resulting changes to the flight profile on the booster and ship, which might become relevant later. In the meantime, let's move on to the more important changes to the propulsion system. For these next two upgrades, we got quite lucky that portions of the installation process of the methane transfer tubes have been performed while the door of the ship bay is open. If not, I doubt we would ever know much about it other than the brief mention of its existence by SpaceX. Out of the two major changes that are relevant to this topic, the most noticeable is the addition of 3 individual transfer tubes for the larger vacuum Raptor engines. On the previous version of the ship, there was a single methane downcomer extending from the bottom of the common dome down to the thrust puck. Near the bottom of the transfer tube, there were 3 pipes that split off the main feed line to distribute fuel to the 3 RVacs. Below this 3-way splitter, the main transfer tube continues down to the thrust puck. At the bottom of this, there is a manifold with 3 outlets for the sea-level engines. Perhaps an important advantage of this design is the fact that all 6 engines were pulling from a common feed line. Even though they will all experience the same pressure spike, it will arrive earlier to the sea-level engines, assuming the total length of the feed lines is slightly shorter. This will cause them to respond faster. Also, it's possible the RVacs will experience greater friction loss in the pipes, which will cause the operating pressure at the pump inlet to be slightly reduced. With that said, any instability introduced by the sea-level engines is likely to be cancelled out by the RVacs or vice versa. Unfortunately, I think this advantage would probably only be factored into future design considerations if you were actually aware that it might be preventing you from having POGO problems. On version 2 of the ship, it appears that SpaceX wanted to split the fuel supply for the RVac engines into their own dedicated feed lines. If I had to guess, this change may be related to some sort of inconsistent propellant supply between the 2 groups of engines. That pressure drop I just mentioned could be something they want to eliminate. This design would give them the ability to regulate flow and pressure for each engine more precisely, which is probably important considering RVacs likely have slightly different operational requirements than sea-level engines. Anyway, with the new design, there are now 4 downcomers instead of 1 for each RVac and a shared downcomer for the sea-level engines. We saw this for the first time during final assembly of Ship 33, which was a huge shocker to say the least. Installation of these transfer tubes requires a special jig to arrange the pipes so the ship can be lowered on top of it. Looking a bit closer, we can see that at the top of each of the 3 RVac downcomers is a flexible expansion bellow to allow the pipes to expand and contract. In the single downcomer design for the V1 ship, there was 1 expansion bellow at the bottom of the downcomer, below the 3-way split for the RVac engines. We believe this still exists, but because the RVac feed lines are now isolated from each other, each one needs its own expansion bellow. We will discuss the potential significance of this shortly. Unfortunately, what we don't know is how the 3 RVac downcomers attach to the aft dome. Because of this, Chameleon Circuit from the Ringwatchers was forced to make a few assumptions based on the previous design. So in this speculative model, they chose to attach them in relatively the same manner they were on the version 1 ships. Basically, there is a curved flange around the end of the pipe that is welded to the aft dome. Now, this is definitely taking us into the smaller details, but it's actually kind of important, which we'll see shortly. Anyway, we now have 4 long pipes going straight from the common dome directly into the aft dome. What could possibly go wrong with that? Well, my immediate thought when I first saw this was that it was going to make recovery of the ship after soft splashdown in the Indian Ocean a lot more difficult. I've always assumed that the reason these ships explode almost instantaneously after tipping over is because of catastrophic flexing in the methane downcomer, causing it to rupture. And now, there are 4 times more of these 15-meter long transfer tubes, 3 of which are half the diameter of the original downcomer. In all honesty, I don't really believe in the concept of a recoverable soft splashdown, especially when we're talking about a 50-meter tall ship. And don't even get me started on the booster. I don't know, for me, this is just one of those things I'd have to see to believe. But playing the devil's advocate and assuming it actually is possible, I just can't help but to think that the chances of the ship being destroyed after tipping over have increased by at least 300%. There was a lot of mission-critical information that would be gathered during a post-flight inspection of the vehicle. It's especially important for the TPS team to finally get their hands on this thing. They have arguably one of the most difficult tasks ahead of them, yet they've also been the most data-deprived group of individuals in the entire Starship program for the last 2 years, if not longer. Beyond that, I'm not sure how SpaceX would be confident enough to attempt to catch up the ship for the first time without being able to verify that the landing hardware won't be compromised during re-entry. Needless to say, I've been very worried about whether this design change would solve a problem in one location while creating more problems in another. As it turns out, this concern may have been warranted, just not in the way I expected. If you recall that short list of factors that amplify the severity of the POGO effect, increasing the length of the pipes was one of them. Instead of roughly 3 meters of pipe extending out nearly horizontally from the main downcomer, we now have just under 15 meters of pipe oriented vertically. That's 5 times longer. While fuel delivery is likely a bit more efficient in this configuration, the lack of a multi-engine dampening effect in the independent RVac lines could be super convenient for amplifying existing behaviors. Especially when you consider the possibility that some of these engines may already have been experiencing miniature POGO without it being detected. The simple fact that all 6 engines were pulling from the combined downcomer may have been enough to suppress the POGO effect to the point that it was considered to be inconsequential as a whole. But by separating the RVac engines into their own dedicated feed lines, they may have unknowingly created the most ideal conditions for POGO to be unleashed in those 3 feed lines. Also, without the presence of the RVacs pulling from the main downcomer, you're left with 3 engines which probably have near identical line frequencies. So it's possible that the chances of developing synchronized thrust responses to pressure spikes in the central downcomer has increased dramatically. Alright, now let's move on to the second upgrade, which is the vacuum jacketed pipes. This change gets a lot less attention, but in my opinion, it's slightly more interesting because it addresses something I've been wondering for years. Taking a look at the original downcomer, we can see that it's basically a pipe with several hoop stiffeners installed along its length for structural support. The part that's always baffled me about this is the fact that on both the ship and booster, there was no insulation around the downcomer. The reason this is confusing is because the temperature of densified liquid oxygen is well below the freezing point of methane. With a full tank of liquid oxygen, this pipe is basically like a tube inside of a heat exchanger. I would expect the liquid oxygen in contact with this pipe to increase in temperature and potentially begin to boil, while the methane inside of the pipe would begin to freeze. This wouldn't necessarily be an issue until the end of the propellant loading process. Until that point, the column of liquid methane is rapidly moving upwards as fuel is being loaded. But once it stops at the end of prop load, I've always assumed that it would begin freezing along the inner wall of the pipe. This is probably less of a problem on the booster, given that the stagnation period where the fluid column is not moving only lasts for about 2 minutes and 50 seconds before ignition, assuming there is no hold in the countdown. So whatever ice forms along the wall probably melts rather quickly once the fluid column begins to move again. The ship, on the other hand, has a stagnation period of about 5 minutes and 50 seconds between the end of prop load and second stage ignition. So this is a lot more time for ice buildup to occur. I'm really not sure how big of an issue this is when it comes to the short duration missions that they have been performing up to this point. The time between burns isn't long enough for the 47 centimeter or 18.5 inch diameter methane downcomer to freeze solid. Beyond that, by the time they perform any orbital insertion or deorbit burns, the LOX tank will be mostly empty. But once they begin developing orbital propellant transfer and storage capabilities, it will become significantly more important to reduce the heat transfer between surfaces. Making sure your methane feed lines don't freeze solid during the hours, days, or weeks of standby time is probably a good idea, hence the need for this upgrade. Vacuum-jacketed pipes are a type of insulated piping system designed for transportation of cryogenic liquids while minimizing heat transfer. These were easily identifiable as they were being installed, thanks to some key features. These pipes consist of an inner pipe and an outer sleeve, or jacket, and are typically made of stainless steel. Inside of the void space is often a layer of insulating material wrapped around the inner pipe. Once fully sealed, vacuum pumps are attached to ports built onto the sleeve and are used to evacuate the void space so that it maintains a permanent vacuum. Depending on the manufacturer, there are several different methods used to join multiple sections of pipe together. One involves using bolt-on flanges with gaskets between them. Another is the bayonet-style fittings, which are secured using clamps. And the most labor-intensive method is to attach a flange near the end of either pipe, weld the two inner pipes together, and then install a sleeve over the joint. After welding the sleeve to the flanges, the void space is filled with perlite for additional insulation before permanently sealing the enclosure. They also make these as flexible stainless steel hoses. The vacuum insulation is excellent for maintaining ultra-low temperatures, minimizing boil-off, and eliminating frost buildup on the outside of the sleeve. This makes them perfect for use in indoor applications where condensation is highly undesirable, various industrial processes where transfer lines may span a long distance, and of course, Starship's next-generation fuel distribution system. So it seems like the upgrade to vacuum-jacketed transfer pipes is the first of many upgrades needed to enable the vehicle to perform long-duration missions. I imagine in the near future, we will see them implement something to reduce boil-off in the tanks that results from radiative heat transfer from the sun, especially if there is no active thermal conditioning system available. Hey everyone, quick interruption here from the comforts of my temporary residence. So, because this episode took place on March 16th, any updates that took place after that date will not be included. So before we continue, there's one thing I wanted to add in relation to the vacuum-jacketed piping. With the recent changes announced to NASA's budget in 2026 and the cancellation of SLS, it's important to note that both the Artemis II and Artemis III missions will still be taking place. This means the need for SpaceX to continue developing orbital propellant transfer capabilities as soon as possible has not changed. Now, depending on where you get a majority of your news from, you may be completely unaware of this massive financial shakeup at NASA. And this is why I'm excited to partner with Ground News again for today's investigation. Ground News is an aggregator that collects news stories from more than 50,000 outlets around the world and combines them into a single, easy-to-read feed. For every story you find on Ground News, you can not only find a high-level summary, but you can quickly sift through the headlines for other news outlets covering the same story. There you can find vital information about that outlet's political affiliations, its factuality rating, and the ownership of the publication. As an example, when these deep cuts to NASA's budget were first announced, I was really curious whether it would be covered in a positive or negative light by the media. After a quick search, you can see that Ground News found 161 different sources covering this topic. In the bias distribution window, you can see that a majority of articles are from left and center publications, with only 19% coming from right-leaning sources. With that said, if you want to know how different news outlets cover the same story, you can easily scroll through and see how the headlines change depending on their affiliation. For a quick high-level summary, the bias comparison tool offers concise comparisons of the details each side tends to focus on. In this case, left-leaning sources tend to look at this as a historic step backwards, while right-leaning sources view it as a necessary pruning of bureaucracy. I'm always surprised what I learn when making these types of comparisons, which is one of the reasons I use Ground News every day. I also love features like their blind spot page, which shows you stories that are receiving disproportionate coverage in one political sphere versus the other. It not only helps me to make sure I don't have these blind spots, but it also helps me to better navigate social interactions by simply making me aware of things that I didn't realize were important to people with different political affiliations. In today's political climate, I think that's more important than ever, which is why I'm a big fan of Ground News, and I think you will be too. In fact, I can even get you a great deal. Just go to ground.news/CSI Starbase to get 40% off the same Vantage plan that I use every day. Again, that's ground.news/CSI Starbase to get 40% off their Vantage plan to help you stay on top of things. But back to the point, how would a change like this contribute to the problems experienced during the two previous flights? Well, when we discussed the Tacoma Narrows Bridge incident a few minutes ago, I listed several factors that affect the resonant frequency of an object. As a reminder, those were material, length, stiffness, and mass. In this situation, by transitioning from a non-insulated single-walled pipe to a vacuum-insulated double-walled pipe, all four of those parameters are guaranteed to be different than they were in the original propulsion system. With that said, not only did they increase the risk of POGO within the individual RVac feed lines and synchronized POGO within the downcomer for the sea-level engines, but it's possible that these vacuum-jacketed pipes may have inadvertently shifted the natural frequency of the entire fuel distribution system so that it's now incredibly close to or matching the frequency of pressure surges and vibrations that were unknowingly being suppressed on the version 1 ships. While any of these situations would be bad enough on their own, if they're all happening at the same time, then the combined effect of these two upgrades is kind of like shooting yourself in the left foot and then stepping on a hidden bear trap as you hop around on your right foot. That would be suboptimal, to say the least. Anyway, hopefully this gives you a good understanding of the upgrades made to the propulsion system of the V2 ships. Although, given the current state of things, that might not be the best way of describing it. On that note, if you would like to pick up one of these Starship 2.0 propulsions t-shirts created by Chameleon Circuit, then visit the CSI Starbase merch store and use code temporary downgrade for a 10% discount. Alright, before we begin speculating on the actual point of failure, let's review the footage and telemetry data from Flight 7 and compare it with the 2 previous flights. We need to take stock of any observations that may be relevant to the situation. Hopefully that will provide some additional clues. It's important to note that the one major aspect of the V2 ship's propulsion system that has not changed is the continued use of the same Raptor 2 engines used on the V1 ship and booster. And because the upgraded V2 ships are being integrated with V1 boosters, there was a noticeable decrease in performance during the boost phase. With 300 tons of additional payload and no upgraded engine performance or extended fuel capacity of its own to compensate, the Delta V capabilities of the booster are significantly diminished. By the time BECO occurs around T plus 2 minutes and 33 seconds, the Flight 7 vehicles are traveling more than 850 kilometers per hour slower, and stage separation is performed 3 kilometers below the previous flights. After booster engine cutoff, Super Heavy drops down to 3 engines. With the heavier ship still attached, the acceleration after BECO should still be around 20% lower. Instead, the acceleration leading up to hot staging is nearly equal, which means the Flight 7 booster is running its 3 remaining engines at a higher thrust output to compensate for the additional mass. Also on Flight 7, it seems like they went back to a weird maneuver that we haven't seen since Flight 2. You can see the booster actually increased thrust prematurely as if to counteract the pushback from the ship. The outcome of this was a bit puzzling because instead of giving the ship a boost, the ship's acceleration actually takes a bit of a dive for a few moments, which we haven't seen before. I know some of you are wondering if some sort of change to the hot staging procedure might be contributing to this problem, but I haven't been able to find anything significant. I know it's not saying much, but when you look at these side by side, you can barely even notice any differences other than the direction of the booster flip. In fact, based on the brightness and density of the sparks spraying outwards from the interstage vents, it seems like the push-off by the ship was actually less violent on Flight 7. But whatever happened there seemed to have an effect on the fluid level sensors in both tanks. If these can be trusted, there appears to be some noticeable fuel slosh in the ship's propellant tanks right off the bat. We don't really see that in the 2 previous flights. Another thing we haven't seen before is the way the level sensors for both tanks seems to fluctuate continuously before they finally stabilize shortly before the T plus 6 minute mark. This could easily be some sort of fluke. However, when we do a side-by-side comparison of the aft flap camera on flights 5 and 7, we can observe some interesting behavior that may or may not be related. When you consider the fact that there is no wind resistance at this altitude, that's some pretty serious vibration going on with Ship 33. And it's not just the flaps. When you look at the clouds in the background, it becomes clear that the entire aft section is shaking. From the view on the forward flaps, you can't really see these oscillations, which may indicate that this is localized to the aft section. When we look under the hood, you can see that the 3 center engines are mounted to the bottom of the thrust puck. So for the most part, all up and down motion is transferred into the dome. The RVacs are also mounted to the aft dome, but they have additional support to help keep the extended nozzle stabilized. For each engine, there are 2 braces mounted to the skirt of the vehicle and attached just above the nozzle extension. Because of this, any POGO vibrations experienced by the RVacs may be transferred directly into the skirt. The flap hinges are mounted to the skirt as well, not too far away from the braces for the 2 RVacs on the front side of the ship. So it makes sense that the vibrations would be transferred into the flaps as well. But this doesn't mean that the sea-level engines aren't experiencing problems of their own, especially considering the first one to fail was the sea-level engine. After returning to that view of the aft flap nearly 3 minutes after the last time we saw it, the vibrations are still ongoing, and we can now see a fire coming from the hinge in the middle of the flap. Unfortunately, we have no way of knowing when exactly this fire started, but it was sometime during that 3-minute period. Shortly after this, another sea-level engine failed, followed by the nearest RVac. A few moments later, the other RVac on the front side of the ship was lost, followed by the last remaining sea level engine. I was really hoping to find something else in the telemetry data that could help identify the moment some of these oscillations began happening, and potentially when they reached their peak as well. But as I've explained in past episodes, you can't really use the unfiltered acceleration curve derived from the raw data because it's far too noisy. So in order to actually see the trends, we have to run it through a data smoother first. Ignoring the two massive spikes in here, which come from data glitches in the live broadcast telemetry, we can see areas where Ship 33 seems to have more pronounced spikes in its acceleration curve. We'll discuss Flight 8 in a few minutes, but when we add Ship 34 to the plot, you can see even more aggressive oscillations in the acceleration. Unfortunately, while I think it's worth showing and taking note of, I don't think we can get anything too conclusive from this data. In reality, I think these vibrations should be happening so quickly that we probably shouldn't be able to pick up on it on such a large timescale anyways. To put that into perspective, in the time it takes to hit the subscribe button, it might experience anywhere from 10 to 50 large oscillations, depending on how fast your finger game is. Along with that, because this is such a massive alteration to the raw values, this evidence would probably be dismissed in court. Alright, so even with all of this information at hand, and I feel like we have quite a bit, it's really not enough to nail down a single point of failure. But unless our understanding of this concept is completely flawed, we should at least be able to narrow it down to a few possibilities. If the design changes to the propulsion system led to previously unexperienced POGO in one or more of the engines, then that means that at some point during the flight, the frequency of oscillating pressure waves begins to match the resonant frequency of some other component in the system. And it's occurring at a location that seems to cause serious propellant leaks. I think the only two possibilities here are either the downcomers or the engines themselves. Now, I could be very wrong about this, but if the frequency of oscillating pressure waves approaches the resonant frequency of the new vacuum-jacketed downcomers, then they might begin to behave like that string from our earlier example. The fundamental mode, or a standing wave with a single antinode, would likely be the most damaging in this case. And the amplitude of those vibrations will begin to increase dramatically with each oscillation until the frequency shifts away from that sweet spot or something eventually fails. Luckily, I think we can assume that any extreme g-forces created by the POGO oscillations are not causing a collapse or rupture of the transfer tubes. If so, liquid methane would leak into the LOX tank, and instead of witnessing a cascading engine failure, it would just go straight to that standby screen as the ship explodes without any assistance from the automated flight termination system. The vibrations alone may provide enough activation energy to initiate an explosion. This means that the leak is probably somewhere outside of the tank. The only way I can imagine for these new vacuum-jacketed tubes to have been the actual failure point is if strong vibrations in the pipes actually managed to crack the weld that joins it to the aft dome of the ship. Given the extreme conditions, it's possible that the weld around the flange could fail, allowing liquid oxygen to begin leaking out of the tank and into the attic space above the aft heat shield. If you remember those expansion bellows I mentioned earlier, they are located at the top of the transfer tube just below the common dome. I think the lack of these expansion bellows at the bottom of these pipes is something that could enable this to happen. The reason I'm considering the possibility of some sort of LOX leak here is because at this altitude, a fire within the attic wouldn't last for very long without a source of oxygen. On its own, a continuous leak of liquid oxygen can cause some major problems, and we don't have to look very far to find an example of that. I'm sure most of you remember the outcome of IFT-2 when Ship 25 was destroyed after an intentional liquid oxygen dump caused a catastrophic fire on the vehicle. Once liquid oxygen comes in contact with one of the preburners, hot gas manifolds, or anything else hot enough to initiate a reaction, it's pretty much a wrap. From there, the highly oxygenated environment would allow the fire to rapidly spread to any exposed electrical wiring and sensors. As these critical components are destroyed, the engines will begin to shut down spontaneously. The other thing to consider is that as far as we know, Raptor 2 is still having the same issue with smaller methane leaks that it's had since day one. This is the reason they use such an aggressive fire suppression system on the booster. I have wondered in the past why the Starship team didn't incorporate an equivalent fire suppression system, but I think the lack of oxygen at this altitude may be part of the reason. It makes sense that they never expected the ship to be farting out LOX in this area. On that note, the second possibility we can come up with is that the POGO experience during this flight occurred somewhere on the engines. That could be in either of the two flexible joints that connect between the aft dome and the turbopumps. Or it could also be in the same locations as the pre-existing methane leaks and is just being made worse by the new vibration environment. I'm sure there are other options for where this failure could be occurring, but these are the ones I consider to be most likely. With this bit of heavy speculation out of the way, let's move on to the next question. Why did the changes made after Flight 7 have little to no effect and potentially make the problem even worse? Well, for one, I think there is a very strong chance that SpaceX did not fully understand the chain of events that led to this failure. This would make sense considering the fact that the Flight 7 investigation is still open at the time of recording this. For the record, I predict a little bit of shade will be thrown in the comments because of that particular detail, but I personally have no issue with that situation. It's clearly within the bounds of the rules set by the FAA to allow flight operations to continue while events of this specific nature are still being investigated. As far as I'm concerned, they make the rules, so it is what it is. Beyond that, I think it's highly probable that there is no way to verify that the situation has been resolved without testing it in flight and praying for the best. But considering that SpaceX clearly had at least a general idea of what was causing the issue, the time between Flights 7 and 8 should have allowed them to install additional sensors to monitor the situation and help gather more data. As far as hardware upgrades, in the aftermath of Flight 7, SpaceX allegedly upgraded the fire suppression system to help displace oxygen within the attic and therefore reduce the severity of any fires that may be present. Honestly, I was hoping to see proof of this change during the static fire test of Ship 34, or even in flight. But unlike the booster, where you can clearly see the massive fire suppression system when it's active, I have not been able to find evidence of its existence on the ship. But that doesn't mean it's not there. The fire suppression system for the booster uses either liquefied or compressed CO2 gas, which is pretty damn cold and clearly visible as a white vapor when the system is active. The equivalent system on the ship uses nitrogen, and depending on the temperature and pressure it's being stored at inside of the COPVs, it may be completely invisible by the time it exits the vents on the aft skirt. Either way, I'm a bit confused by this upgrade because I can't imagine it being very effective in this situation. For one, the total volume of space being purged inside of the booster's engine shielding is actually pretty comparable to the volume in the attic of the ship. On Super Heavy, the suppression system covers the containment boxes around the outer 20 engines, the aft cavity above those enclosures, and the cylindrical shields around the 13 center engines. This sounds like a lot, but on the ship, the aft heat shield spans the entire cross-sectional area of the 9-meter skirt, and considering there are only 6 engines, there's a ton of empty void space up here. Therefore, it will probably require a similar volume of gas to continuously displace any oxygen or methane that may be present, if not more. The CO2 storage tanks on the booster are incredibly large, and they stretch the entire length of the strakes on the front side of the vehicle. Given that there are no external tanks on the ship, the fact that most of the COPVs are located in the nose cone, and the fact that the ship was already fully stacked when they announced this change, I think the most likely location for additional nitrogen tanks would be in the aft cavity of the ship, mounted to the inner wall or the aft dome between the RVac engines. This is the only location that wouldn't require new plumbing to be installed on the exterior of the ship, which we definitely would have noticed. So if these tanks exist, they probably have significantly less capacity than the equivalent system on the booster. Mounting the tanks in this location does have the added benefit of decreasing the volume in the attic just a little bit. Even so, I would be surprised if it's capable of running for the full 6-minute duration of the main burn for the ship. If that's the case, then it would only be activated after a fire is detected, instead of being used as a preventative measure to stop the fire from occurring in the first place. If a sustained liquid oxygen leak is given the chance to cause fires in this area, it may already be too late by that point. Working against the compressed nitrogen fire suppression system is the fact that the expansion ratio of densified liquid oxygen is several orders of magnitude higher. So if it's not already running before the LOX fire is initiated, it's hard to believe it wouldn't be completely overwhelmed from the moment it's activated to the moment the AFTS is triggered. The sustained combustion reaction, combined with the liquid oxygen rapidly expanding into a gas, and the fire suppression system can quickly cause the pressure inside of the attic space to increase dramatically. In order to relieve the pressure in the event of a fire, there are vents installed on the walls of the attic. These aren't anything special, just holes punched into the ring section. On the previous version of the ship, there were 16 of these holes on the front half of the ship. Most of them were located just above the false ceiling. On Ship 33, the first V2 ship, they redesigned the vents and moved them to either side of the QD. After Flight 7, they doubled the amount of vents with the intention of making it easier for gases to escape the mostly enclosed attic space. But did this do anything to help the situation on Flight 8? No. Not at all, apparently. Leading up to Flight 8, It seems like SpaceX decided to make some adjustments to the flight profile on the ship in order to help it avoid recreating the same operating conditions that caused it to fail previously. They got rid of whatever weirdness happened during hot staging on Flight 7, and things looked a bit more normal other than the weird bobble on the prop level sensors, which actually seemed a bit worse this time. Another detail I noticed in the telemetry was that it seemed like they wanted to keep the thrust output slightly below the level of the previous flight up until the 5-minute mark, where acceleration began to match up again. It's hard to tell if this is actually from adjusting the thrust output or purely a result of the different trajectories. On Flight 8, they seem to sacrifice a bit of speed for additional altitude. The interesting thing about this, if we compare the suspected fuel slosh behavior on the level sensors, it still seems to be doing the exact same thing that happened on Flight 7, and even stabilizes back out at the same time, which is within this 1-minute interval where accelerations were nearly matching. After this point, the Flight 8 ship returns back to running at a slightly reduced thrust output. Once again, it's difficult to determine whether this was intentional, or if in this case, the engines were beginning to underperform. When we look at the engine bay camera, we can see that there was a fire raging in the attic again, which somehow made its way through the false ceiling. One thing we can say for sure is that this nitrogen suppression system is barely an inconvenience for these types of fires. Many of you likely noticed the glowing pipe on the side of the RVac to the left. After speaking with some folks on this subject, this might be an indication of insufficient methane flow to the cooling loop in the nozzles. Given the complexity of these engines, when things aren't running perfectly, the eventual shutdown is normally more of an explosion. An RVac rud has potential to cause considerable damage given that the power heads have no shielding to contain the shrapnel. They used to have identical shielding as the center engines back in the days of Ship 20, but for some reason the Starship team got rid of them when they introduced the false ceiling. So it's possible an explosion of an RVac may not only damage surrounding engines, but could send shrapnel through the aft dome, resulting in a cloud of oxygen spewing from the back of the vehicle. Interestingly enough, this incredible footage from Astronomy Live seems to show a massive loss leak after the explosion we saw on the onboard camera. Now, there are many ways this can happen, so we can't really say it's a result of a puncture of the tank. Did a violent engine failure cause the liberation of the heat shield panels and adjacent engines? Or did the fire and subsequent overpressure of the attic destroy the engines? Without the release of additional onboard footage, your guess is as good as mine.
Alright, now let's move on to the next question. Why was this issue not able to be detected during pre-flight testing? Was that 60-second static fire test performed by Ship 34 leading up to Flight 8 completely useless? Well, I think one of the biggest problems here is that this issue is very difficult to detect without being able to replicate the exact conditions. To truly have confidence with how the vehicle's propulsion system will perform during all phases of flight, you need to be able to perform full duration static fire testing. Without that, the only other way to verify that things are working as intended is to just launch it and see what happens. This has been SpaceX's approach for the Starship program from day one, which is one of the things that not only sets them apart within the spaceflight industry, but is arguably a major deviation from their own procedures with Falcon 9.
Every Merlin engine, first stage booster, and upper stage vehicle that comes off the Falcon 9 assembly line in Hawthorne is shipped off to SpaceX's McGregor testing facility, where they're strapped down to a test stand to undergo long-duration static fire tests. In the early days of F9 development, the boosters performed tests that would last for around 140 seconds, which is the typical duration of the boost phase burn. The same was true for the second stage, which has a much longer burn time. During these tests, the engines will also ramp up and down in thrust level as they would during a real mission. In recent years, as they have gotten more confident in the consistent manufacturing quality of Falcon 9, the duration of these tests has been reduced by about 50%. Booster tests are now around 77 seconds in duration, and Stage 2 tests are around 260 seconds long. So, minus the ability to simulate changes in atmospheric pressure experienced during ascent, for the most part, they are able to confirm that the vehicle will perform as expected throughout the entire powered flight regime. Once the boosters are flight proven, they are basically trusted to perform the same every flight thereafter. The only time they are subjected to additional static fire testing is if they are used on a crew mission or integrated with 2 other boosters on a future Falcon Heavy launch. Those are usually just short duration tests to verify everything is functioning correctly. Back to Starship, every new Raptor engine used on a Super Heavy booster or ship undergoes the same static fire testing process. As far as we know, they almost always perform a full duration burn, sometimes lasting as long as 300 seconds.
But while engine performance may be flawless on the test stand, that doesn't necessarily mean it can be expected to perform the same once integrated onto the vehicle. The conditions are completely different once you have multiple engines firing at the same time. In fact, we probably shouldn't even refer to these integrated hot fire tests as static fires at all, because they are actually pretty dynamic. The conditions are constantly changing with each passing second. As an example, the resonant frequency of a downcomer pipe completely submerged in liquid oxygen will change as the fluid level decreases. So if you perform a test while the tanks are full, everything may seem fine. But if you were to do the same test while the tank is filled to a quarter of its capacity, the results can be very different. Unfortunately, a true full duration test for both the booster and Starship is simply not possible at this time. There are two reasons for this. The first is water capacity. To perform a long duration test, the deluge system must have enough water available for the system to continue running for at least 150 seconds for booster tests and roughly 360 seconds for the ship. From our observations, there is only enough water at the launch site to run the system for about 40 seconds, or 25% of what is needed for full duration. And we now know that the ship's static fire stand has a capacity of at least 60 seconds worth of water, or 16% of full duration. I should note that even if 4 or 5 times the amount of water were available, SpaceX would not want to be performing 150-second booster static fire tests. Not only does it create a sustained cloud of superheated steam that engulfs the entire launch site, but with each passing second, the surface of the water-cooled steel flame deflector plate is slowly being worn down. It's entirely possible that a 150-second test would eat through enough of the steel to render it unsafe to operate. To put this into perspective, after 7 launches, this booster bidet system has only experienced about 60 seconds of direct contact with the most destructive part of the super heavy exhaust plume. So 150 seconds is equivalent to about 21 launch cycles worth of wear and tear. The second reason a full duration test is virtually impossible is because the clamping mechanism for both the ship and booster are not designed to withstand the type of mechanical stress they would be forced to endure. This is why the liquid oxygen tanks are filled as high as possible to weigh the vehicle down and keep the thrust to weight ratio to a manageable level that the clamps can handle. Even if the thrust is kept as low as possible, around 40 to 50% throttle, once the propellant level drops below a certain point, the gradually increasing thrust to weight ratio will begin to put a ton of stress on the clamp mechanism. Luckily, the inability to perform this type of test on the booster hasn't really been an issue, as it's performed remarkably well during the ascent phase for every launch since IFT-1. Unfortunately, the same cannot be said for the version 2 ship. So what's the solution to this problem? Well, without a massive increase of water capacity for the deluge system, or dramatically beefing up the hold-down clamps, there isn't much that can be done. Well, at least not if they want to test this on a ship that is expected to become a flight-ready vehicle. On that note, there is one option that could allow them to simulate the second half of the ship flight profile with a reduced propellant load if we look at past examples. For those who weren't around for the suborbital hop phase of the Starship program, it's my pleasure to introduce you to SN4. On second thought, meet SN5. SN5 was one of the first test articles with any resemblance of a real ship to perform a 150-meter hop test. Unlike previous test articles, SN5 had 2 full-size propellant tanks. To simulate the mass of a nose cone, there were 2 rolls of stainless steel mounted to the top, each weighing about 13 tons. Taking some inspiration from this, if SpaceX wanted to be able to perform a long-duration test of the ship, they could do so using a test tank with the updated V2 propulsion system. To be clear, this would realistically only happen if the problem gets even worse on Flight 9. So if they decided this is a critical design flaw for the ship, then this might turn into an emergency situation. Instead of taking the time to build a test article, they would probably just chop the top off of Ship 36 and convert it for this purpose. They've already done similar vehicle-to-test tank conversions in the past. After removing the nose cone and the flaps, they can add some reinforcements to allow them to place a cap over the top of the methane tank and anchor it to the ground. As you may have noticed earlier, this is exactly how they handle static fires on Falcon 9 boosters. The good news is, they already have a cap that can be used for this purpose. It would just require a bit of alteration to the test stand to add hard points for the cap to anchor to. As far as the water capacity limitations for the flame trench, there are creative ways to get around that as well. Instead of a full duration test, they could perform 6 65-second static fires, and on each consecutive test, fill the tanks just above the level where they ended on the previous test. A test like this would allow them to stitch together the overlapping sets of telemetry data and basically wind up with a dataset that simulates the full flight profile for the ship, or maybe just the region they care about between 2 and 4 minutes into the main burn. So, did SpaceX make a mistake by taking such a major shortcut in static fire testing? Well, you could definitely argue that, but in my opinion, I don't think so. Despite everything I just explained, I just don't think it's possible to truly recreate the same conditions on the ground. For one, the ship has a unique problem that the booster doesn't really have to deal with: vacuum engines. As the name implies, these engines are optimized for vacuum operation. When tested on the ground, there are braces installed around the nozzles to help stabilize them. Without these braces, the nozzles could easily tear themselves apart during extended testing. Unless you have a vacuum chamber large enough to hold a 35-meter tall test article, there is literally nothing you can do to simulate in-flight conditions for these engines. Second, with the ship clamped down to the test stand and a cap over the top to hold it down, the vibration environment would be totally changed, as would the resonant frequency of the vehicle. The third and final reason is more important than anything else if I understand this concept correctly. When we discussed the physics behind the POGO phenomenon, we identified the cycle of events that caused this problem. Pressure waves traveling downwards through the propellant at the speed of sound cause spikes in pressure at the inlet of the turbopumps, which surges fuel to the engines, resulting in a brief increase in thrust output, followed by a spike in acceleration, which creates another pressure wave and starts the cycle over again. The key word here is acceleration, and it's kind of hard to accelerate if you're strapped down to a test stand. In my opinion, without a specialized test structure that gives you the ability to simulate these conditions, there's only one way to know whether or not you have a POGO problem, and that means you gotta send it. Now, maybe I'm crazy, but I think Nicki Minaj may have actually predicted this more than 13 years ago in that song where she said starships are meant to fly. Anyway, that's what makes this situation so difficult. Once you realize you've contracted this disease, you have to stop and identify the possible causes. After you have it narrowed down, you have two options: give up and go back to what was working, or try to solve it. While reverting back to the single downcomer design of the V1 ship might seem like the safest way to avoid the problem, it actually presents several issues. For one, they would still likely want to keep the vacuum jacketed design because it seems to be very important for long-term propellant storage. And if they do that, there is a possibility that they can still end up with the same problem if it turns out that the resonant frequency of the vacuum jacketed piping is more of a contributing factor than the independent RVac feed lines. The other problem is that this can't be done without scrapping every single ship currently in production. So not only would they be taking an automatic 6-month delay after scrapping all of these vehicles, but it would all be for nothing if it ends up failing again anyways. Now, based on the fact that they clearly aren't planning to scrap anything at this point, it's safe to assume that giving up and going back to what was working is not even considered as an option for them. Instead of avoiding the problem, it's in their best interest to come up with a solution to make the new propulsion system design work. In my opinion, there are 3 ways they can approach this. The first option is to improve the ability for the affected component to be able to withstand the current level of vibrations being experienced. This could take the form of additional structural reinforcements like bracing for the downcomers, adding flexible bellows to the bottom of the RVac feed lines, assuming they don't exist already, and maybe adjusting the amount of flexibility allowed by the bellows. They could also find ways of dampening vibrations on various parts of the engines with the hope that it will stop leaks from forming. The second option would be to attempt to change the resonant frequency of the part that's failing. But first you need to know what that frequency is. On that note, if I had to guess, before SpaceX performed that 60-second static fire test, they probably installed a bunch of accelerometers and other sensors in various locations on the ship to allow them to observe anything they think may be contributing to the problem. So while performing that 60-second test was probably useless if the goal was to try to recreate in-flight conditions and detect the problem, it's actually super valuable data if they use it as a baseline to compare against what actually happens in flight. After Flight 8, I think it's safe to say that they probably know a lot more than they did after Flight 7. This hopefully includes the amplitude and frequency range of pressure spikes at the turbopump inlets, the corresponding thrust increase from those pulses, and potentially the resonant frequencies of every component involved in the failure. Whatever the pressure wave frequency was at the moment the leak was detected, well, there's your magic number. With that information, they could try things like adding reducers or expansion chambers, changing the diameter or thickness of the vacuum jacketed downcomers, or maybe even adjusting the annulus pressure of the vacuum jacketed pipes. The problem is, while either of these solutions could potentially allow the ship to survive long enough to reach SECO on the next flight, a simple change like increasing the amount of payload on the following flight could cause it to come right back. In my opinion, these solutions are more like Band-Aids. And don't get me wrong, sometimes Band-Aids work out great. The fire suppression system on the booster is a perfect example of that. But in this case, there are far too many random variables that can alter the effectiveness of this Band-Aid for it to be worth the risk. Returning to that metaphor from earlier, if your foot is already caught in a bear trap, it's best to find a way out that doesn't involve shooting yourself in the foot again. And considering Raptor 2 has already been bailed out more times than Mike Tyson, I think it might be necessary for them to take a different approach this time. With that said, the best course of action, without a doubt, is to address the problem at its source. In other words, instead of treating this as a vibration environment to be factored into the design specifications for other components of the vehicle, SpaceX needs to POGO-proof the engines. Period. Now, I'll let that sink in for a second. Alright, now this is by no means a simple thing to accomplish, but luckily there are plenty of historical examples of how this was solved on other rockets. I think we have enough time, so we might as well take a look at some of them.
Actually, just talk to the big guy upstairs. Can't swing you that extra time. Hour's up. We're gonna start pulling windows. He also told me to tell you, you don't gotta go home, but you do gotta get the f*** out of here.
The first time NASA ever identified POGO as a threat to spacecraft and their crew was during the Gemini Titan II program. Titan II was a ballistic missile in development for the US Air Force, which was intended to carry nuclear payloads. In order to meet the aggressive timeline set by President John F. Kennedy, NASA wanted to piggyback off of Titan II's development and adapt it for human spaceflight missions with the Gemini spacecraft. After purchasing 12 of the missiles, they worked alongside the Martin Company to improve the performance of the vehicle to make it suitable for their needs. The Air Force was already trying to get vibrations on the vehicle within an acceptable range for their payloads, but NASA asked them to take it a step further. Compared to the Mercury spacecraft that came before it, NASA planned for the crew to have much more involvement in piloting functions during the powered phases of flight. For this reason, it was important to make sure the conditions inside of the spacecraft were suitable for pilots to be able to perform the tasks required of them. So, while the intensity of vibrations experienced at different locations on the vehicle might be well within structural limits and could therefore be ignored, they also had to consider human limitations. During the first test flight in March of 1962, the first stage vehicle experienced longitudinal vibrations going from 10 to 13 Hz for a period of 30 seconds. The maximum amplitude of these vibrations reached plus or minus 2.5 Gs, which is a total magnitude of 5 Gs. This was considered excessive for the safety of the payload, which had a maximum limitation of 2 Gs. But for the crew, the limitation set by NASA was half a G. So this was 10 times greater than the acceptable limit and would have resulted in a rather uncomfortable experience that would impair their ability to operate the vehicle or address emergency situations during this period. At the time, engineers had no idea what the source of vibrations was. It wasn't until the fourth test flight where they increased the operating pressure of the fuel tank and noticed that the POGO amplitude was cut in half. This is when they realized that oscillating pressures in the propellant feed lines was most likely the cause of the issue. For reference, in the Titan II missile, the oxidizer tank was mounted above the fuel tank. After examining what turned out to be an incorrect mathematical representation of the system, engineers decided that they needed to focus on the oxidizer feed lines, which were much longer than the fuel lines. Because the oxidizer transfer tube has to pass through the fuel tank before splitting off into separate feeds, the change in fuel tank pressure was able to affect conditions inside of the oxidizer feed lines. So they began to focus their efforts on finding a way to reduce the pressure wave from the tank to the oxidizer pump inlets. In response, they installed a vertical surge suppression standpipe charged with gaseous nitrogen in each of the oxidizer feed lines. This is very similar to a water hammer arrestor. At the top of the standpipe is the pressurized nitrogen, which is compressed anytime a pressure wave reaches the pump. This reduces the size and strength of the pressure wave. Unfortunately, this did not have the desired effect, and actually increased the POGO oscillations from a total magnitude of 1.25 Gs up to a record 9 Gs. That was 5 times higher than the acceptable limit for military payloads and 20 times higher than the limit for manned missions. This forced an early shutdown of the engines, and the vehicle was lost. As it turned out, they realized that the frequency of vibrations through the oxidizer feed lines was partially canceling out the oscillations on the fuel side. So by eliminating them, they actually amplified the feedback on the fuel feed lines. As a result, they realized that they might need POGO suppression on both the oxidizer and fuel feed lines in order to solve the problem. But it would take some time for them to implement. In the meantime, They removed the oxidizer standpipes, increased the tank pressure, and swapped out the steel feed lines for aluminum. They didn't understand it at the time, but the change in material reduced the POGO vibrations on the 9th mission. The result of the next 12 flights brought the vibration levels within acceptable limits for the Air Force, but they were still too high for NASA. Finally, after redesigning the oxidizer standpipes to account for the updated mathematical model and installing mechanical accumulators on the fuel lines, they had their solution. This combination allowed them to finally bring the POGO vibrations within an acceptable limit, recording a maximum amplitude of 0.11 Gs on the 22nd flight test. This was just over 1 year and 8 months after they began working on the problem. After 2 more successful missions with the suppression system installed, Titan II was finally declared suitable for human flight missions in January of 1964. Unfortunately, while Titan II was the first vehicle that required NASA to dedicate a massive amount of resources towards solving POGO problems, it wouldn't be the last. While NASA was dealing with the POGO problems experienced during the Gemini program, they were also simultaneously developing the Saturn rockets, which would be used to take humans to the moon as part of the Apollo program. As they began unmanned missions with Saturn V, they soon encountered a similar POGO issue. But this time, they actually experienced it on both the first and second stage vehicles. Given that they had the same requirement of no more than plus or minus 0.25 Gs of oscillation for crew exposure, they took this problem very seriously. The Saturn V rocket with its massive F1 engines on the first stage and J2 engines on the second and third stages was a far more complex vehicle and required them to dedicate a lot more resources to solving the problem. At one point, they had a special task force of 1,000 engineers working to find a solution. Similar to the Titan II, the Saturn V's oxidizer tank was situated above the fuel tank. It had 5 massive feed lines to transfer liquid oxygen through the fuel tank to the turbopumps. Just before the pumps is a pre-valve which controls the flow of liquid to the pumps. This actually looks incredibly similar to the V2 Starship, except the tanks are reversed. After Apollo 6, they retrofitted the fully assembled first stage rocket to allow them to use helium gas from the tank pressurization system to fill cavities in the LOX pre-valves. This essentially converted the valves into accumulators, which successfully detuned the system. This solution was verified during ground tests somehow, which allowed them to clear the vehicle for manned missions before Apollo 8. On that mission, they discovered the same problem on the second stage vehicle. This time, the 4 outer engines were fine, but the center engine experienced severe POGO. The center engine was unique because of the flexible crossbeam structure it was mounted to. A spike in thrust would bend the crossbeam and compress the flexible joints in the feed lines. This increased the fuel pressure and resulted in a surge in thrust. After the pressure and thrust returns to normal, the crossbeam would bend back down and decompress the feed lines. This causes a drop in inlet pressure to the pumps, which reduces thrust even further. Any cavitation that forms during this time can quickly cause damage to the pumps as well. Eventually, the pressure returns to normal, the engines accelerate forward again, and the cycle continues. During this flight, they recorded a maximum vibration of 9 Gs on the center engine, which was getting close to the structural limit of 15 Gs. After the problem was first detected, they came up with a temporary solution to allow them to continue flying while a permanent fix was being developed. They knew the worst of the vibrations were occurring around 468 seconds into flight. So on Apollo 9 through 13, they decided to shut down the center engine 75 seconds early and extend the burn using the 4 remaining engines. They hoped this would help them avoid the worst of the problem, which was expected to occur 50 seconds before shutdown. But during the Apollo 13 mission, the center engine experienced an acceleration of 34 Gs, which occurred way earlier than expected. Luckily, the engine shut itself down before the second oscillation, or the vehicle would have potentially been destroyed with the crew on board. As many of you know, this was actually just the beginning of the huge clusterfuck of problems that occurred during that mission. Anyway, after Apollo 13, they implemented the permanent solution and installed a helium bleed toroidal POGO suppressor for the LOX side of the engine. This was a bit different than the fix for the first stage because they had a lot less space to work with. So they drilled holes through the existing feed lines just above the flexible bellows and encased it in a drum that was pressurized with helium. Other than the perforations through the feed pipe, this would actually look very similar to a short vacuum-jacketed pipe section. This LOX feed line accumulator successfully brought an end to POGO problems on all future Apollo missions. Wow, this is some straight up bullshit. Seriously couldn't wait 10 more minutes? Well, at least I don't have to worry about falling out the window.
Anyway, 2 years later, with the insane events of Apollo 13 fresh in their minds, NASA began development of the Space Shuttle orbiter. With the Space Shuttle, they planned to fly crew on the very first mission. So Aerojet Rocketdyne dedicated a lot of resources towards designing the RS-25 engine to be as POGO-proof as possible. The POGO suppression system they developed for this was a lot more complex than the accumulators used on Titan II and Saturn V, and it required a lot of advanced testing for them to get this right. Part of the complexity came from the fact that there were 4 separate components of the integrated vehicle, which resulted in a lot of weird asymmetries that had to be factored into the structural analysis. The propellant supply for the orbiter's 3 RS-25 engines came from an external tank via a detachable umbilical system at the bottom. They wanted to keep the center of gravity as high as possible, so the much heavier liquid oxygen tank was mounted above the larger hydrogen tank. So similar to the Titan II and Saturn V, the oxidizer has a much longer feed line to reach the engines. But one thing that worked out in their favor here was the fact that the density of liquid oxygen is more than 16 times greater than liquid hydrogen. This meant that any pressure waves traveling through the hydrogen would be significantly weaker and could basically be ignored. Another major difference here is that they weren't trying to remediate the issue on a completed vehicle, which allowed them to integrate it directly into the engine design. They really had no other choice but to do that, however, because of a unique feature of the RS-25, which has both a high and low pressure turbopump on each side. The low pressure pumps were mounted to the vehicle, while the high pressure was attached to the engines. They initially planned to install the system before the low pressure pump, until they realized it wasn't guaranteed to prevent pressure waves from reaching the high pressure pump. Because of this, they decided the most effective solution would be between the high and low pressure LOX turbopumps instead. This thing is actually pretty damn large. I believe you can see it right here in this image. It's described as a spherical container the size of a basketball, charged with hot, 400-degree gaseous oxygen for most of the flight, with a helium charge used prior to engine start. The high-pressure liquid oxygen is separated from the gaseous oxygen by a baffle plate to prevent the liquid oxygen from splashing up into the gaseous oxygen and condensing the bubble. It was designed to attenuate LOX flow oscillations into the high-pressure turbopump in the 5 to 50 Hz frequency band for a smooth flow rate of LOX into the high-pressure turbopump. The mixture of gaseous and liquid oxygen is continuously bled from the suppressor to control the gas volume and maintain the feed system dynamics that prevent POGO. Then the mixture was reintroduced into the feed line upstream of the engines to condense all of the gas back into a liquid. If you didn't understand any of that, don't worry. The point is, it's super complex, and implementing a more state-of-the-art design like this would probably take a lot longer than the typical 1 to 5 months between Starship launches. The testing procedure for the RS-25 suppression system was pretty advanced as well, and involved pulsing the propellant supply to the engines to simulate a wide range of oscillations they could experience during the flight. They actually managed to do this before they ever flew the vehicle for the first time, so I suppose it actually is possible to accomplish this with ground testing. But it's far more expensive than the fly and fix approach. This is part of the reason why it cost NASA around $5.8 billion, or just over $20 billion in today's money, to develop and launch the first space shuttle. I'm sure that after hearing these stories, some of you may be wondering, so what, did SpaceX seriously ignore decades of NASA research on this issue? Well, it might seem like it at first, but as it turns out, this isn't their first rodeo. They actually have a POGO suppression system on both Falcon 9 and Falcon Heavy.
POGO bleed verification.
But if they already have experience developing this type of system, and should therefore know it's a good feature to have, then why is it not already incorporated on the Starship? Well, if we look at the timing of when this was introduced on the Falcon 9, it might help answer that question. While there is no widely available information about this, the first mention of POGO suppression techniques being used on Falcon 9 was on its 18th launch during the MonacoSat mission in April of 2015. You can hear the call out right around the T-3 minute and 29 second mark.
POGO accumulator bleed vent?
The mention of a POGO accumulator bleed vent is accompanied by a short purge at the bottom of the vehicle. Given the proximity to the engines, it's safe to assume this venting is related to pre-charging the POGO accumulator system with gas. Without knowing any details about how it works, this sounds very similar to the description of the process for Saturn V. Anyway, instead of accepting that this launch was the first usage of the system, I searched through previous missions to see if the same vent was present. At the same time in the countdown during the previous ABS-3A Eutelsat mission, we can see an identical vent. In fact, I could see it on every launch where the location of the vent was actually visible until I reached the CRS-2 mission, which was the last of the V1.0 Falcon 9. So it turns out that this system was first introduced on their 6th launch during the Cassiope mission in September of 2013. This demonstration flight featured a lot of firsts. It was the first vehicle to be integrated with the new upgraded Merlin 1D, the first version 1.1 Falcon 9, the first mission for a private customer, the first time launching from Vandenberg, and, the first time running water through this deluge system apparently, and even though the vehicle was lost, it was their first attempt at a soft landing of the booster in the ocean. While the Merlin 1D had a lot of important performance upgrades, I think the introduction of a POGO suppression system may have been a crucial step for gaining certification to fly military payloads. Based on the examples we just discussed, this would likely be important for crewed missions in the future. In fact, on their 8th flight during the TICOM 6 mission, the US Air Force used telemetry data from that flight as part of the certification program. For all we know, this may have actually been a requirement for future crew resupply missions carrying sensitive research equipment, and even some of the private customers they immediately began executing contracts for. SpaceX didn't end up launching their first military payload until a year after TICOM 6. Although we have no additional information on this topic, it's possible that the process of dialing in this system caused some delays to their certification process. With these considerations in mind, it makes sense that with Starship, they were probably well aware that they would eventually need POGO suppression incorporated into their engines, but at this point in the program, it may not have been very high on the priority list. That would kind of be like trying to include solar panels on the first ship used for IFT-1. Any combustion instabilities detected during the 5 suborbital hops and 5 integrated flight tests for the V1 ships were not severe enough to exceed structural limitations or cause failure of their propulsion system. So a much bigger concern for them was stopping all of the methane leaks, preventing engine ruds, and developing an integrated cooling system so they can ditch the heat shield on the booster. On that note, perhaps they were already planning to do this on the second revision of Raptor 3. If so, they almost got away with it. Almost. Anyway, with these historical examples in mind, what have we learned and what predictions can we make about how SpaceX will solve this POGO problem on Starship version 2? Well, the common theme about the various solutions is that they all involve installing some sort of accumulator after the pre-valves and ideally as close as possible to the turbopump inlets. Also, with the exception of the Space Shuttle, which used low-density hydrogen for fuel, this suppression system appears to be needed on both the fuel and oxidizer side of the engines in order to maximize its effectiveness. Even though the solution seems pretty clear, based on how long it took for NASA to solve it on other vehicles, it's definitely not as easy as it sounds. For one, they need to find a place to put it. The first option would be to take the approach of installing it directly onto the Raptor 2, just like they did with the RS-25. But in my opinion, that's probably out of the question. For one, as far as engines are concerned, SpaceX has already shifted most of their focus towards Raptor 3 development. The idea of circling back to create an integrated POGO suppression system for an engine they're planning to phase out in the very near future would be a massive waste of time. They're better off attempting to do this with Raptor 3. But to rely solely on that approach would mean scrapping all existing ships because they're more than likely incompatible with the new engine. The problem with that is, as far as we can tell, Raptor 3 development does not appear to be moving as fast as SpaceX might have hoped. Over the past few months, we have seen many Raptor 3s destroyed during static fire tests at McGregor. It's possible these were intentionally pushed beyond their limits, but it's also equally possible that they're having legitimate problems with the new engine right now. The fact that they haven't shared any videos of it yet makes me lean towards the latter option. With that said, I think it's safe to assume that it could take anywhere from 6 to 12 months to get Raptor 3 ready, especially if they need to incorporate a new component that doesn't exist in the current design. But this estimate is highly dependent on the amount of resources they decide to throw at it. To expedite the process, they can put a halt to everything else and then gather their entire staff of engineers working on Merlin and Raptor, along with the Falcon 9, Falcon Heavy, Dragon, Super Heavy, and Starship propulsion teams, and have them combine forces until a solution is found. Just throwing this out there, might even be a good idea to kidnap Tom Mueller or something. Considering NASA had 1,000 engineers working on Saturn V POGO, this isn't all that unreasonable. I think we can scratch this option off the list though, because not only is it clear that SpaceX has no intention of standing down from launches for the amount of time it would take to pull this off, but I have a feeling it's simply not possible to install this directly on the engines in the first place. The reason for this is because of the location of the turbopumps on both the Raptor 2 and Raptor 3. There's literally no room to put anything above these. On top of the LOX turbopump inlet is a flexible bellow which I would have to imagine is off limits for a whole list of reasons.
The methane side is the same as well, except that flexible component gets added on later. There are 5 different versions of these, depending on the location it's installed on either the booster or ship. And that takes us into the second option, which would be installing this on the pipework that connects between the turbopump and the pre-valves. This might actually not be too difficult on the methane side of things. For the RVacs, there is a short vertical header pipe between the pre-valve and the inlet for the fuel turbopump. And for the sea-level engines, there is a much longer horizontal header pipe, which would probably be a lot easier for them to integrate the system onto. But in both cases, it would have to be on a section of pipe that doesn't interfere with the flexible bellows. Assuming they do not want to touch these header pipes, the final option would be to install the accumulators on the vehicle side plumbing at the bottom of the vacuum jacketed transfer tubes. This would mean cutting out a section of the outer pipe and then resealing it on both ends so it's able to maintain a vacuum in those sections. Next, they could drill holes through the inner pipe and then install an enclosure around it. This was a solution used on the Saturn V's J2 engines, and as a reminder, would look similar to this example I showed earlier. Because this is inside of the LOX tank, it's important to make sure that it doesn't freeze. But helium gas inside of the accumulator might be enough to prevent that from happening. While this is a pretty major surgical operation to perform on a completed vehicle, I think this might be the most realistic option. They wouldn't be able to do this for the individual sea-level engines, but they could install another helium accumulator just above the flexible bellow in the combined downcomer. Luckily, this wouldn't be the craziest thing the remediation team has had to pull off over the last few years. The only problem is that the industry-recognized best practice is for the POGO suppression system to be located after the pre-valve and as close to the turbopump inlet as possible. So installing this on the vacuum jacketed pipes would not be the most ideal location. Alright, now for the LOX side, which again we are assuming would be necessary and is unfortunately a lot more difficult to integrate. For the RVacs, the portion of pipe after the pre-valve is a very short elbow section that passes through a cylinder, which is part of the structural reinforcements of the aft dome. Having to work around this would leave them with a very small section of pipe to incorporate some type of accumulator. It would probably be easier to put it before the valve, but I don't know how that would impact its effectiveness. For the sea-level engines, this is even more interesting because now you have to consider the splitters that allow the engines to swap from the main tank to the header tanks during the landing burn. If they want to use one system to handle both modes of operation, then it would have to be integrated at the bottom of this Y section. But I doubt that's even possible. The next option would be to address them individually. For the main tank feed line, it could be somewhere in the short curved section that goes into the side of the large diameter inlet manifold for the RVacs. For the header tanks, there is a very short section of pipe above the valve available. All in all, that makes 4 or 5 different variations of this system that they would need if they chose to cover all bases at the same time. And even if the overall design concept for each of them is the same, tuning this system for an RVac may be different than what's required for a sea-level engine. The good news is, there's several layers to this option, and they don't necessarily have to be completed at the same time, even though that would probably be the best way to reduce the possibility of another in-flight failure. To keep the flight testing campaign moving forward, they could just make these changes on the methane side only for the next flight, since it's way easier to change out some bolted-on pipe sections. This way, all remediation of any fully assembled plumbing inside of the tank would be avoided for now. Furthermore, they could just focus on the RVacs or just the sea-level engines depending on whichever one they have identified as the biggest problem. Assuming they want to minimize delays to the launch schedule as much as possible, they could even just attempt to throw an upscaled version of the Falcon 9 accumulator in there instead of spending a lot of time up front developing a carefully tuned system from the start. If it works well enough to get them through the second stage burn, then they can just iterate on the design from there like they do with everything else. Each successive vehicle will have a better version of the system as they use data from each flight to make changes to the next ship in line. This would give them more time to make changes further down the vehicle assembly line to accommodate the other variations that would have been too invasive or potentially require them to scrap all existing aft section hardware. Okay. Based on some of the things I've seen y'all post on X over the last few months, I know that some of you may think scrapping existing hardware is probably still the best way forward. And honestly, you might be right. Time will tell. But in my opinion, I think that at this point in the program, they would rather fail at least 2 more times before they seriously consider that option. And at that point, they would basically wind up at the same place anyways, so I truly believe that this is the best way forward. But based on historical precedent, it makes sense that it will take time to implement the permanent solution. So if I had to guess, at least 6 to 9 months, and they may have to go through the same process again
once the V3 ship and Raptor 3 engine are introduced. The only way we will know this is the path they decide to take is if they happen to mention POGO suppression or the word accumulator in their next pre-flight announcement. The important thing to keep in mind is that because they will likely take incremental steps to build up to the final solution, this is still a fix and fly strategy. Therefore, there is a very high probability that it will fail again on the next flight. So, I don't want to say expect another failure, but just don't be surprised if it happens. The good news is, another catastrophic failure just means that they have another massive treasure trove of data that helps them evaluate how the incremental changes affect the behavior of the system as a whole. The final thing to consider is that while they work towards a permanent solution, there are still things they can do to avoid the conditions that led to the failures on flights 7 and 8. Just like the decision to shut down the center engine 75 seconds early on the Saturn V second stage. In other words, they can make a significant change to various operational parameters on Ship 35 for the next launch and pray that it survives long enough to reach SECO. There are a ton of things they can try here based on things that have been shown to affect the performance on other vehicles, so I'll just list off a few possibilities that could potentially get mentioned during the Flight 9 broadcast. 1. They can adjust the internal tank pressure of either the LOX or methane tanks. This, of course, has its limitations because it needs to be within a certain range to keep the turbopumps of the Raptors happy. 2. They can inject helium bubbles at the top of the propellant feed lines. There is a chance that they are already doing this, but if not, doing so may change the line frequency. 3. Reduce the flow rate of fuel, and by extension, the thrust of the RVac engines below the level it was when they experienced the worst of the POGO problems. This will also affect the flight profile to some degree, but they can adjust accordingly. 4. Adjust the temperature of the propellants. Increasing the temperature would reduce the density and mass. This would not only reduce the strength of the pressure waves, but it should change the line frequency as well. When we compare the telemetry from flights 7 and 8 to the 2 previous flights, we can see that for some reason, SpaceX is apparently limiting the booster's acceleration after max Q. When you look at the sharp decrease in slope on the acceleration plot, this is super obvious. It's important to note that they also do this on flights 5 and 6, but it happens about 30 seconds earlier with the V2 ships. I'm not sure if this is purely to conserve fuel for boost back, or if they're trying to avoid some kind of structural failure on the booster from high G-forces. Considering they're already through the point of maximum aerodynamic pressure, this seems unlikely. Either way, if they extend the burn of the booster for a few more seconds, then they can reduce the amount of fuel loaded onto the ship. This would change the mass of the vehicle throughout all points of the powered flight regime and is likely to affect the amplitude and frequency of the POGO oscillations in the process. But extending the ascent phase burn would of course consume the remaining fuel needed for boost back and force them to perform a downrange water landing similar to the flight profile used by Falcon 9 when it lands on the drone ships. While losing out on the opportunity to recover booster 14 for a second time might be less than ideal, there's a chance that recovering the ship might be slightly more important. In my opinion, if they chose to go with this option, that would be a sign of how desperate they are to stack as many cards as possible in Ship 35's favor. These are all things I will be listening and looking out for during the next flight. Hopefully there will be something to confirm some of these theories. But as I said at the beginning of the episode, it's important to remember that all of these conclusions are based on incomplete information. So it's possible we could have gotten some of this completely wrong. But we did the best we could to explain this with the information available to us. My goal for this episode was to provide some context to how difficult of a situation this is in order to temper any expectations that may be unreasonably high. But on that note, if there is one company on the planet that's repeatedly shown they have the ability to find solutions to mission-critical problems, and doing so on ridiculously short timescales, it's definitely SpaceX. With that said, if anyone from the Starship Propulsions team happens to watch this, I want to wish them good luck. No matter what happens on the next flight, I'm sure y'all will block out all of the noise and stay focused on the goal as always. Alright, well, I think it's finally time for me to leave this studio that's been our headquarters for the past few years. But before I do, I want to give a huge shout out to Virtual Space 3D and my producer Geoff, who have made all of this possible. I also want to give a special thanks to Chameleon Circuit, The Space Engineer, Andy from the Starbase Sim video game, Seabass 3D, and Ryan Hansen Space for the custom renders and animations, along with everyone else whose content was used in today's episode. As you can tell, it takes a massive amount of coordination to put these together. So if you would like to support what we do here, please consider becoming a member of the channel or a monthly supporter on Patreon. For those interested in downloading the Starbase Sim video game, I will put a link to their website in the description. And finally, If you want to pick up one of these 3D printed Starship models, make sure to check out morethan3d.com, where you can find all kinds of amazing 3D models that you can either order or print out yourself if you have a 3D printer at home. Last but not least, thank you to Ground News for sponsoring today's investigation. Alright, well, I guess it's officially time to say goodbye. Well, rest in pieces. It's been real.